quite a number of questions. But for now, it's now my pleasure to introduce Professor Stefan Rahmstorf from University of Potsdam, Institute of Physics and Astronomy. So Stefan is also head of Earth System Analysis at the Potsdam Institute for Climate Impact Research. So Stefan's work focuses on the role of the oceans in climate change. So he has been teaching physics of the ocean as a professor at Potsdam University since 2000. Stefan is a member of the Academia Europa and served for several years on the German Advisory Council on Global Change. He was also one of the lead authors of the fourth assessment report of the IPCC. In 2007, he became an honorary fellow of the University of Wales, and in 2010, a fellow of the American Geophysical Union. In 2017, yes, he was the first scientist outside the US to be awarded the Climate Communication Prize of the AGU. So it's a great honor to have you there. So Stefan, the floor is yours.
Yes, hello everybody. It's a pleasure to be part of this exciting webinar. And I want to talk about the Atlantic overturning circulation, the AMOC, and I'll jump right into it so that we have enough discussion time. This diagram already shows key features of the AMOC, mainly the surface currents in red with an overall northward transport, and the deep current in blue, the North Atlantic deep water returning to the south at about 2 to 3 kilometers depth down below the ocean surface. And obviously, this works like a central heating system with warm waters flowing north, giving up their heat to the atmosphere in the northern latitudes, and then sinking down to depth, returning to the south as a cold, deep current. Just have to click further. Yeah, here's another view of this, which is actually part of a movie animation, but with Zoom, it's not so good to show movies. So it doesn't add anything to the previous image. There was a very nice article last year in the New York Times about the dangers of abrupt ocean circulation change in the Atlantic, which I really recommend also because of its fantastic graphics that the New York Times team now has quite a track record producing great interactive internet graphics. And I want also to use this New York Times article advertising a little bit the fantastic initiative climatefeedback.org, which for those who don't know it yet, it looks at the media coverage of climate change. There's actually now also one on health issues. Together they're called Science Feedback. And what it does, it asks a whole bunch of experts in the area that is covered by some media article, whether this article is scientifically credible or not. And often they expose some really wild, unscientific climate skeptics articles. In this way, they have been able to get some retractions of wrong articles by writing to the editors of the newspapers and magazines. And this New York Times article has also been evaluated by experts, and it was given a very high to high scientific credibility rating. This is an overview of the overturning circulation caused by density differences in the ocean, which just is there to show that it's not only the Atlantic, but there is a worldwide overturning. But Christoph has already showed Wally Broker's classic image of this. This is a somewhat more elaborate, not quite as highly simplified version, which in orange shows the areas of deep water formation of the global ocean. And in green, the kind of high salinity, and in light blue, the low salinity areas of the surface ocean, because of course the density depends on temperature and salinity. And you see that the sinking happens not in the high salinity, but in the low temperature areas. So the temperature effect on density dominates over the salinity effect. But salinity does play an important role, as we shall see later on. Now, a first a very important hint on abrupt climate change comes from paleoclimatic data, notably the Greenland ice core data, which are shown here in blue. And in green, we see some sediment data from the Sargasso Sea, which show basically very similar time evolution as the temperature over Greenland, which just hints at this not being some local effect over Greenland. It's a kind of regional effect of the whole North Atlantic area, as those working in paleoclimate know very well. And the numbered events are the Dansgaard-Oeschger events, which represent sudden warmings. And the red boxes, they are the so-called Heinrich events, which basically show the release of big iceberg armadas into the Atlantic Ocean. You don't see those registered in these particular data here in the curves very, very much, except that they tend to occur during the stadial, the cold phases of the glacial. You see them in other areas, for example, sediment cores of Portugal, for reasons that I will show in a minute. The best explanation that I think we still have for the Dansgaard-Oeschger events is a sudden ocean circulation shift, and from the normal glacial state, or we could call it a stadial state, where the deep water formation occurs to the south of Iceland in the open North Atlantic. And occasionally during these Dansgaard-Oeschger events, convection starts up in the Nordic seas, and so this conveyor belt circulation, this heat transport, jumps further north into the Nordic seas. One very strong piece of evidence for this is, for example, the sudden increase in salinity near Iceland seen in the sediment cores when synchronously when these Dansgaard-Oeschger events happen. And the fact that it has to do with heat transport across the hemisphere, across the equator, is also shown by the seesaw behavior between the Greenland ice core and the Antarctic ice core, which very strongly hints at this bipolar seesaw effect, and therefore the key role of sudden changes in the Atlantic overturning. Now, when, then I won't go into the Heinrich events, but these Heinrich layers are basically showing huge amounts of glacial deposits transported by icebergs, so-called ice-rafted debris in the sediments, but they are synchronous with a breakdown of the Atlantic overturning circulation. So the idea that the AMOC can dramatically change and abruptly change is well documented in the Earth history. This has happened quite a number of times during the last ice age. Now, if we look at the present evolution of global temperature, then we see, of course, that the entire globe has warmed, but there is one notable exception that resists this warming, like that Gallic village from Asterix, and that is this region in the subpolar North Atlantic, which has actually cooled in the last 100 years or so. And just another view of this fact is this nice image of NASA that they put out a few years ago, which was just showing the temperature anomaly of a 5-year period. And while the whole globe was basically warmer than normal, this cold blob in the northern subpolar Atlantic really sticks out as a really exceptional big signal. So what is the reason for this? We can turn to model simulations for the cause of this, and here is the GFDL CM 2.6 climate model, which has a particularly nice high-resolution ocean component to the climate model, which you can already see at the fine structure of the eddying there in this temperature change pattern that you see here. And it has a very realistic ocean circulation. And what this image shows is the response to a CO2 increase in that CM2.6 GFDL climate model. And you see a very peculiar anomaly pattern, and the anomaly is here defined relative to the global mean sea surface temperature change. So everything blue has warmed less than the average ocean surface. Everything in orange red has warmed a lot more than the average ocean surface. And you see this cold region south of Greenland is really very remarkable again. And some of it actually has cooled, some of it has just warmed less than average of that blue region. But there's a second part that is this excessive warming along the North American Atlantic coast. And both these phenomena of this pattern, the blue part and that red part of North America, have the same reason, namely a slowdown of the AMOC in that model. And there's a number of papers that theoretically explain why, when the AMOC slows down for reasons of vorticity conservation, the Gulf Stream moves inshore, which you can nicely see in the CM2.6 climate simulation, but you can also explain it by dynamic ocean theory and also by simplified models. So this pattern that you see here in the Northern Atlantic is what we called in this paper with Levke Cesar as a first author, a fingerprint of an AMOC slowdown. And Levke went to look at the trends in all the available sea surface temperature data sets since the late 19th century. And so she found this trend pattern. And if you look at the North Atlantic part, you clearly see this same fingerprint pattern for an AMOC slowdown, except it is a little bit more fuzzy because, of course, we don't have the super high resolution of observational data for the last 100 years or so, as we have in the climate model. But I think this is very strong evidence that the AMOC has actually already slowed down. And by comparing it to the model simulation, we calibrated this pattern to represent about a 15% slowdown of the AMOC since the late 19th century, most of which actually has happened since the mid 20th century. In a more recent paper, again with Levke as a first author, we showed a compilation of different paleoclimatic records from around the North Atlantic. The location of these data is shown in the little map in the top right corner here. And the different curves are shown in the different panels here. The left-hand side shows about 1,500, 1,600 years of time, and the right-hand curves zoom in onto the time period since the late 19th century. And especially if you look at the longer-term evolution, you see that all these records have one thing in common. They are pretty stable up until the 19th century, and then these curves all go down, which is independent support for the idea that the AMOC has actually slowed down, because all these different publications argued that these particular sediment records are indicative of the AMOC strength, and they are of very different type, like these curves by Tornelli, that is sorted silt, so it's a grain size of the sediments at the area where the North Atlantic deep water passes over the ocean surface and so on. They are very different, but they show quite a consistent picture. And we now have a little update in press at Nature Geoscience, which just zooms in onto the changes since the mid-20th century and compares these sedimentary records with some shorter-term data that are trying to reconstruct the AMOC since the 1980s, or in case of the RAPID project, just measure it since 2004. And you see again that this actually presents quite a consistent picture if you account, as we did in this diagram, for time lags. The changes you see in the temperature of the subpolar gyre, or the productivity in the subpolar gyre, lag the measured rapid AMOC by 6 years here in this diagram, whereas the sortable silt data from the deep branch lead by 6 years, which makes sense if you look at model simulations of the changes in the AMOC first appearing in the North Atlantic deep water at the bottom before you actually measure them as the full overturning signal. And so again, we see a nice agreement with very different types of approaches and data sets. And if you align them, you find leads and lags that make physical sense completely very well. So I think there is pretty strong evidence that the AMOC has been weakening since the 19th century. Now, one of the reasons for the weakening, in addition to just surface warming, is the input of fresh water. Fresh water dilutes the salinity and therefore reduces the surface density, which inhibits the sinking and thereby the overturning. And whereas temperature has a negative feedback, which means that if you warm the surface, you weaken the AMOC, which tends to then cool the surface. So there's a kind of negative stabilizing feedback. Salinity has actually a positive destabilizing feedback, because if you add some fresh water, you reduce the salinity, the AMOC weakens, and that reduces the salinity even further, because it is the AMOC which brings high salinity subtropical waters into the high northern latitudes. And so you weaken the AMOC, you reduce salinity, and that weakens the AMOC even further. And such a positive feedback, that is always a possibility for a tipping point. And Christoph has already explained in quite a bit of detail on the kind of tipping points. And he has already shown this very simple picture of a ball that is sitting in some kind of cup here, or bowl. And this is actually quite I think, a very good illustration of a tipping point, because that ball, if you push it a little bit to the side, it tends to roll back to its stable state, except here where the arrow points, you have a tipping point. If you push it beyond that point, it's not going to roll back. And this is also a good diagram to explain one way of looking at an approach to a tipping point, because if the landscape here, this bowl in which the ball rests, becomes more shallow, then it will take longer for that ball to roll back into its central stable position if you just perturb it a little bit to either side. And the more flat this landscape comes, the less quickly does the ball roll back. And that leads to larger fluctuations just by random noise forcing, and it leads to a longer time for these fluctuations to die down, which can be used and has been used for many nonlinear systems to indicate the proximity to a tipping point. But let me first, before I get back to this particular point, point you to this overview that we published about a bit more than 2 years ago in Nature on tipping points with Tim Lenton as the first author. And basically, we looked at a number of tipping points, updating the classic Lenton et al. Paper, which was a kind of seminal description of such tipping points. And it has there the Atlantic circulation at the center of a network of tipping points, and one of the key issues debated in the tipping point scientific world now in the community is the interaction of different tipping points, and the question, can they trigger one another in a kind of domino effect? And we wrote in this article that the clearest emergency, climate emergency, would be if we are approaching a global cascade of tipping points. And for example, for one of these cascades, the Greenland ice sheet, of course, adds meltwater. It has its own tipping point where the Greenland ice sheet will be doomed for total loss, 7-meter sea level rise, and a lot of fresh water going into the North Atlantic. That can trigger the Atlantic overturning to cross its tipping point, which in turn can trigger shifts in the tropical rainfall belts, affecting the Amazon rainforest, which has its own tipping point, or affecting the Antarctic ice sheets. The Atlantic tipping point can be very clearly found already in the most simple box models, like a Stommel type 2-box model from the 1960s. And it can be found in fully 3-dimensional global ocean circulation models. And it looks like this if you look on the x-axis at the freshwater going in, and on the vertical axis, the strength of the AMOC. Then we're now on that upper branch with a strong AMOC of something like 17 swerdrops or 18. And if we add more freshwater, we will move that point to the right where we are, and it will hit this Stommel bifurcation at some point where it will just not be able to sustain itself because of that positive salt advection feedback that I mentioned. And then the AMOC will die down, and it will not return even if you return to the previous climate. You'd have to go quite far to the left on this diagram before that off state becomes unstable, and the AMOC would kickstart again. This is not something that would happen in human lifetime. If we kill the AMOC, that will be it for generations. Now, the big question, of course, is how close are we to a tipping point? And Christoph already mentioned the fact that although for many systems we understand that there is a tipping point and why there is a tipping point, it is very hard to tell where this tipping point is, because we are talking about highly nonlinear physics. And nonlinear systems are characterized by a strong dependence on the exact conditions. And so there have been many attempts in recent years to find out how close are we to an AMOC tipping point, and they are making use of that fact that when you approach a tipping point, the variance of the system increases in the presence of noise, which is always there by weather variability. And the response to that noise grows bigger and bigger as the system becomes less and less stable. Now, just by an increase in variance, you still can't tell how close you are to the tipping point. You might see, okay, the variance is increasing, but you don't know at what level of variance will you be at the tipping point until it's too late, basically. But my colleague Niklas Börs from the Potsdam Institute has published a very scary paper, I would say, in Nature Climate Change last year, looking at a number of indicators of these time series that I showed earlier, some of those from Levke's paper, Paleoclimatic time series, and other reconstructions of the AMOC, like the one based on the cold block temperatures. And he has looked at this lambda parameter, which is the time it takes for a perturbation to die down, like the time it takes for that ball in that cup to roll back to the center. And when that lambda approaches zero, the time basically becomes infinite. And at that 0 point, that is where the tipping point is. And so when you look at these time series, on the left panel there at the bottom left, that's temperature-based reconstructions. And on the bottom right panel, it's salinity-based reconstructions. You see these trends since the 19th century of approaching the zero line at the top. So that indicates, according to all these time series, we are moving towards a tipping point. But this analysis also tells you how far away it is. It's when the trend line crosses zero at the top of the diagrams. And you see, of course, there is a spread between the different indicators, but some of them, like these blue curves in the left-hand panel, are reaching zero around the year 2000 already. So this is really, it has scared me quite a bit that this would indicate that the tipping point is quite close, or maybe already there even. So I haven't heard some criticism that invalidates this analysis. I would love to, actually, because I don't want to believe this is true. This would be really bad news for humanity. So if you know any good reason why we don't believe these results, please tell me. Christoph mentioned that many climate models don't show this tipping point being crossed in the 21st century, but there's also a whole bunch of literature on why climate models overall probably put the AMOC in the wrong stability regime and have an AMOC that is too stable compared to what data from the ocean observations indicate. And one reason for that could be that there are problems with getting the exact salinity distribution in the Atlantic right. And a very interesting paper about 5 years ago by Wei Liu and colleagues corrected the salinity biases in a climate model in the Atlantic. So it's like a kind of a bias correction to get the correct salinity. And with that model, they found that if you take a standard global CO2 increase scenario, the AMOC does actually collapse within this century. And they call this an overlooked possibility of a collapsed AMOC in a warming climate. Overlooked because most models tend to have an AMOC that is too stable. At least that is my reading of the literature. And with that, I'm at the end, and I thank you for your attention. Sorry about the little advertisement for these books that I have co-authored, and please follow me on Twitter if you like, and also join Scientists for Future. That I think is a very good initiative, and I look forward to the discussion. Thank you very much.